Today we will discuss a basic overview of VXLAN or Virtual Extensible Local Area Network. So there are different challenges that were there in our legacy networks. So the very first challenge was or is the spanning tree protocol, right? Because if we have a large data center, then there will be a lot of block ports in the network, right? Because spanning tree, just to avoid the loops, it will block some of our ports, so we will not be able to utilize those ports. Hence the full bandwidth will not be utilized. Secondly, the thing is that because in today's era we have a limitation of VLANs. If we are hosting a large number of customers, then uh, the number of VLANs or 4094, it cannot be sufficient to cater those customers or large number of customers. Hence, if we are hosting a large number of customers, we need more VLANs, or we need uh, something like VLANs that can help us avoid this particular issue. So now you can see that there were other technologies also that are used to overcome this spanning tree problem. For example, we have VPC, right? So using the VPC, we can avoid the block ports, because in VPC all the ports are in forwarding state, right? There are other benefits of also there for VPC, but you know that VPC can be configured between two devices only, so it is limited to two devices. Then there comes fabric path, right? So as the number of endpoints within the layer 2 network expanded, it becomes impractical for all the switches within the network to learn all the uh, endpoint MAC addresses, right? Let's say if we have a large network, then if one host is connected to one device and another host is connected to, let's say, 10 or 12 switches behind, then all the switches within your network, they learn about the MAC addresses, right? Then we have the protocols like fabric path, wherein we can overcome this particular problem, that all the devices are not going to learn about the MAC addresses. Only the relevant devices will learn about the MAC addresses, right? And we also have ISIS running into the core of fabric path. So no block ports, and ECMP can also be achieved using fabric path. But problem with fabric path is that we have that this particular technology is Cisco proprietary. Only Cisco devices support fabric path, right? That is why we need something else, and that is for we have VXLAN, because VXLAN is open standard. We have a layer 3 core, so we do not need to worry about the spanning tree protocol or the block ports, because we are not running spanning tree. So all the interfaces will be having the layer 3 interfaces, and we can and all the interfaces will be participating. So there is no block port concept into VXLAN fabric. So we can also achieve equal cost multipathing. So we will discuss about it, how it will be achieved. Now, there are more than 16 million broadcast domains. Okay, in traditional network, we used to have around 4,000 VLANs, right? But now we have a concept of VNI, or VXLAN network identifiers. So it is having a 24-bit value. So that is why it supports around 16 millions broadcast domains. So in case of VXLAN, the broadcast domain is the VNI, or the VXLAN network identifier. That also, as because we are having the layer 3 core, so there is no loop kind of thing in the core network or within the fabric, VXLAN fabric. And it can handle large east-west traffic flows, because in today's era there is hell lot of east-west traffic going on within our data center. Even if you're accessing, let's say, any website, Facebook or Twitter, so in the background there is a lot of communication, east-west communication going on between your your app and database servers. There is a lot of stuff going on between them. So to cater those heavy traffic flows, VXLAN comes into picture. Okay. So now the question comes in that on a particular device or if a specific customer, we can only create, we are saying that VLANs will be mapped with the VNIs or the VXLAN network identifiers, and into the VXLAN, the broadcast domain is VNI. If we are doing a one-to-one mapping of VLAN to VNI, and VLAN can only be 4094, then what is the logic behind 16 million broadcast domains? Okay. Now let's see this example. Let's say we are hosting a data center wherein we have 5 switches. Okay. So on switch 3, let's say we terminated customer A. Customer A is having VLANs from, let's say, 2 to 1000. Okay. On switch 4, we have terminated customer B. He is asking that I need VLANs from, let's say, 1006 to 3500. Okay. So we assigned VLAN from 1006 to 3500 to customer B. Now another customer comes in. He says, okay, I need around 2000 VLANs, and specifically from VLAN number 3000 to 3500. Now you can see that we have a problem because we have already configured VLAN 3000 to 3500 on customer B. Now you cannot configure these VLANs. Otherwise, you can see that customer B and customer C, they'll be having a common broadcast domain, and then the traffic can leak between the customer B and customer C. So what is the solution? So what we can do now, say this, what we will do, we will map, let's say VLAN 2, we'll do a one-to-one mapping. Okay, so for customer A, we says that okay, VLAN 2 is having VNI 4002, VLAN 3 4003, something like that. Okay, so in this example, I took only 2 VLANs. I will show you that how the traffic is not going to mix between the customers. So let's say all customer A, B, and C, they want VLAN 2 and 3. Okay, or they are running VLAN 2 and 3. For customer A, I will define on switch 3 that for VLAN 2, it is having the VNI 4002. For VLAN 3, it is having the VNI 4003. On switch 4, you can see for customer B, I defined that VLAN 2 is having VNI 5002. Similarly, on customer C, I defined the VNI 6002 for VLAN 2. Now you can see that because we said that the broadcast domains are the VNIs. Okay. Now switch 5, if it received any traffic for VLAN 2, it will check, okay, what are the other switches that are part of this VNI 6002. Let's say there is another switch 6, wherein also we have customer C connected. Then switch 5 is going to send traffic to only switch 6, which is part of VNI 6002. Now you can see that even though we are using the same VLAN number for all the customer, but their broadcast is not going to be leaked, right? Because the mapping of VLAN is with VNI, and the broadcast domain that VXLAN will work upon is the VNI or VXLAN network identifier. So for different customers, we'll map a different VNI number so that multi-tenancy can be achieved. I'll show you when we'll discuss about multi-tenancy. I'll show you with practical that we'll use the same VLAN for different customer, and once we'll do the capture, Wireshark capture, then you will see that we are not receiving any broadcast traffic, or we are not receiving the inter customer traffic, okay, the bump traffic. So it will never happen that I send one traffic into VLAN 2 and all the switches which are part of VLAN 2, they are receiving it. It will never happen in case of VXLAN, because here the broadcast domain is the VNI. So now I think I hope that it is clear now what is the logic behind 16 millions the VNIs. Even though we can configure only 4,000 plus VLANs on a switch on a device, then what is the logic behind 16 millions broadcast domains, right? All right. Now there are overlays and underlays. So I will not spend much of time. I do not want to go into too much detail to explain what is underlay, what is overlay. I am not going to do any configuration related to GRE as you can see in the picture. So because in this course, my focus is purely on into VXLAN. So I do not want to unnecessarily extend the videos. Okay. So, but having said that, I will give you a basic idea about overlays and underlays. You can see a simple example. We have router one, okay. On the left hand side, on the on the right hand side, we have another device. You can consider any router, Palo Alto, like in this scenario. Then we have the ISP terminated on router one and this Palo Alto network on the right hand side. We have the ISP cloud in between. So normally you can see that behind router 2 we have the LAN network, which is in on left hand side we have 192.168.1.0 network. On right hand side behind Palo Alto we have 192.168.2.0 network. So now because we have a public network in between the within the ISP, we cannot communicate. So these two LAN networks, different LAN networks, they cannot communicate directly, right? So what we can do, we can use the concept of tunnels. Like in this scenario, we have GRE tunnel, right? So you can see that in this example, behind R1 and R2, we have private networks. So on one side, we have R1 and R2. So let's say we have any protocol running. Let's say on one side, we are running BGP. On R2 and Palo Alto also with the ISP. And within the cloud also, let's say we are having BGP. Okay, so that these public IPs 11.1.1.2, it can reach to 12.1.1.2, which is the public IP of Palo Alto WAN interface, right? Now what we can do, we can form a tunnel or a GRE tunnel, and the GRE tunnel will be having the source interface, this WAN interface 11.1.1.2, and the destination interface will be the Palo Alto network, this network, right? So what I mean is that if we talk about the underlay and overlay, the underlay is this one, right? So for example, we are the protocol which is responsible for the public IP's reachability, right? Reachability is of the tunnel. So for R1, the tunnel source will be 11.1.1.2, right? For Palo Alto, the tunnel source is 12.1.1.2. So R1 needs to reach to 12.1.2 and Palo Alto needs to reach to 11.1.1.2, and we are running into the WAN, we are running BGP. So the BGP in this scenario, it is known as it will be called as underlay connectivity, right? Because this is providing us the reachability of the tunnel source, or where our tunnels are terminated, right? And this GRE is working as a overlay, which is forming a tunnel between R1 and R2 so that these LAN subnets can communicate to each other, right? So this is how the underlay and overlay concept works. And the same scenario we'll see in case of VXLAN. So I will not go into too much detail of underlay and overlay. I just wanted to show you that what exactly is the logic behind overlays and underlays. Okay. Now you will see the underlay and overlay in case of VXLAN. So you'll be having the spine switches, we'll be having the leaf switches, and then we'll be having the endpoints. Between our leaf and spine switches, we will run some IGP protocol so that their tunnel endpoints, like if you go here, so we have the tunnel endpoints in our scenario in GRE, we have 11.1.1.2 and we have 12.1.1.2, so that they can be reachable, right? Similarly in this, we'll be having the tunnel endpoints for each device. So we'll run the any IGP like OSPF, ISIS so that their tunnel endpoints can be reachable. And VXLAN will be working as an overlay solution in this case, so that all the endpoints which is having these which will be connected to your leaf switches, they'll be able to communicate to each other using that overlay. Okay, so overlay will be VXLAN. So overlay in data center environments, they are referred to as network virtualization overlays. Okay, devices that perform encapsulation and decapsulation of VXLAN traffic are known as VXLAN tunnel endpoints. Okay. Then we need to consider MTU also, because VXLAN had extra 50 bytes of overhead before sending the packet. Hence, we need to make sure that MTU is increased. Okay, so you can see that in this diagram, or that we have a original layer 2 frame that is received from the host. So after the original header, you can see we have a VXLAN header, which will be of 8 bytes. Into the 8 bytes, you can see that it will contain 3 bytes or 24 bits of VNI field. Okay, and there are other informations also, but the main stuff that we need to focus on is the VNI. You can see that it will contain a 3 bytes of VNI field, which will be having 24 bits. So using these 24 bits, you can see that it will be possible for 16 millions of values. Then it will be having the UDP header, which is of 8 bytes. So source port, it is going to choose randomly. That is why we'll be able to see the ECMP or equal cost multipathing, and the destination port will always be 4789. You see, in our case, when we are using the VTAP addresses, so in all the communication, no matter how many hosts you have behind the leaf switches, maybe you can have thousands of hosts, but when VXLAN is going to encapsulate the traffic in the source IP, it will always be the source IP of the uh, leaf switch, which is encapsulating the traffic, and into the destination IP, it will always be the destination leaf IP. Now you can see that if there are thousands of hosts between, let's say, two leaves, then the source IP or the outer source IP and the outer destination IP, they are not going to change. So we do not have much uh, to consider for ECMP. You can see that when we are doing, let's say we are having the port channel, there are a lot of load balancing mechanism that we used to have. We can have a combination of source MAC, destination MAC, source destination MAC, source port, destination port. But here you can see that always the communication is between two leaf switches, and source tap address and destination tap address will always be same. That is why um, UDP was considered for ECMP, because randomly it is going to using the remaining portion of your headers, it will use everything, and it will generate a random source port number for each flows, and that is why ECMP will be considered. You will see that it will do ECMP very perfectly. Let's say if a leaf switch it is having two links connected to two different spine switches, so perfectly it will do ECMP, which is possible using the UDP header, because it will choose the source port randomly, and based upon those it will send the traffic to the available upstream links. Destination port for UDP, it will always be 4789, which is reserved for VXLAN protocol. Then we will be having the outer IP header, which is having 20 bytes, and outer MAC header, which will be of 14 bytes. So you can see that 8 bytes, 8 bytes, 16 plus 20, 36 plus 14 bytes. Now you can see that we have extra 50 bytes of information. In our normal cases, you can see that in our layer 2 can accept only a maximum of 1500 bytes of information from layer 3, but now we have more information. That is why within the fabric now, if you keep the Ethernet links as with the normal MTU, then your communication is not going to work, okay, because of the extra information that VXLAN is putting into. So make sure that your MTU size is increased on the within the fabric devices, okay. There is one note here. This will make more sense once we progress with this series, but it's a simple note that into the VXLAN header, it will, as I mentioned, that it will keep the VNI information. So there are two type of VNIs that we'll study in this course, layer 2 VNI and layer 3 VNI. So just remember that VXLAN field can carry only either it will carry layer 2 VNI or it will carry layer 3 VNI, but it cannot carry both at the same time. So then we can discuss about the IP schema that we can design accordingly. Okay, so let's see one example that if we use /30 subnet mask between the point-to-point links between spine and leaf switches. Okay, so /30 will be having total 4 IPs, right? So two IPs will be usable and two IPs will be for broadcast. So let's take an example of 4 spine and 40 leaf switches. So 4 spine and 40 leaf switches, they will be having 160 point-to-point links, right? And for each link, we are using how many IP addresses? We are using 4 IP addresses, right? So for 160 links, there will be 460 IP addresses, and plus 44 IPs we need for the loopback interfaces. So total IP addresses that will be used if we configure /30 mask between our leaf and switches, so we need to spare at least 684 IP addresses. See a second example. If you use /31 mask, which will be having only 2 IPs, right? Both are usable, no broadcast IPs or network IPs. So in that, if you take the same example, we'll be having 164 links, but now because we are having only 2 IP addresses plus 44 loopback IPs, now you can see we'll be having only 364. We need only 364 IP addresses. Okay. There is one more efficient method. We can use the IP unnumbered concept. Okay, so for all the loopbacks and interfaces, we can use the same IP. So 4 spine and plus 40 leaf switches, total 44 devices. So only 44 IPs will be required if we consider the IP unnumbered schema. So according to our design, we can configure the IP schema. So I have shared with you all the IP schemas that can be defined. You can use /30, you can use /31, or you can go with the IP unnumbered concept. So that was the basic about VXLAN. Then in our next section, we'll start discussing about the ingress replication, how traffic flows within the VXLAN. I hope you like this video, and thanks for watching. See you in the next section.